Okay, sorry about that. The stream got disconnected. Okay, so one second. Okay, sorry about that. It got disconnected. So we were saying the time to the highest point P, and that is suppose our T H, and that will be equal to our velocity V divided by G. And the height of the highest point highest point, and that height we have taken as h, which will be equal to our v square upon 2g. And so if you want that the projectile or balls from A and B, if they want to be colliding at P, then it has to be satisfying two conditions. Okay. Therefore we can write that condition for collision and which basically means that at time t of h, which is equal to our v upon g, the left ball means basically from point A the left ball should be at height h. So this is the first condition, that's the vertical distance traveled by the ball from our point A should be equal to h, and the horizontal distance traveled should be equal to our d. Then only collision is going to take place at point P. Okay. So these are the two constraints about this. So let us now discuss our vertical motion of our left ball. Vertical motion of left ball, which is from point A, and we can write its vertical position we can write its equation as our y of t will be equal to our initial velocity in y direction minus half gt square. And we know that our time t is our v upon g and y is our height h. So we substitute it and we get that our y is our h, and h is our v square upon 2g. So we can say h is equal to v square upon 2g is equal to our u of y. Time is our v upon g minus 1 by 2, and this comes as v upon g whole square. And if we simplify it, we are going to get that our u of y is equal to our v. So this is the vertical component of the velocity for our ball which is launched from our point A. Now similarly we are going to discuss the horizontal motion of the ball. So we can say that our horizontal motion of left ball which is launched from point A, and we can write its equation for horizontal position, general equation. So we can say that our horizontal position, that is our x dependent upon time t, will be equal to initial velocity in x direction multiplied by time t, and time t is nothing but th. Okay, so we already know this value, and therefore we get, and x of t is equal to d. That will be our distance traveled. So we can say our d is equal to our u of x. Time is our v upon g. Therefore we get that the velocity component in x direction will be equal to our gd upon v. And we are also going to find out the minimum speed for the left ball, that's our u. Therefore we can say that we need to minimize the speed of u. Sorry, not speed of u, but speed u. Therefore we can write that our u will be equal to, this will be u square, we can write this as a ux square plus uy square. Okay, because for point A this is our u x component and our y component. So we substitute ux and uy, we get this as a u square. Ux is our gdv upon whole square plus, and u of y is our v square. Therefore we are going to minimize it with respect to v, okay, and equate equal to 0. Therefore we can write this as a d of our dv will be equal to our v square plus g square d square upon v square, and this we are going to put equal to 0. Now it's almost done. We get this as a 2v minus this will be our g square d square, and we get this as a v cube multiplied by 2 is equal to 0. Therefore we can say that 2 we can just ignore it, and we get this as v4 is equal to g square d square, or we can say that our value of v is equal to square root of g d. So this is our value of our v. and we need to find out our u minimum. Therefore we can say that at v is equal to gd, we can write that our minimum value of our x component will be our square root of our gd, and our y component will be equal to square root of gd. Therefore we can say that our u minimum will be equal to ux square, that is our gd, and plus uy square, that is also our gd and its square root, giving us twice gd. So this is the value of our minimum value. So we come to the next question. One second. It's not charging. Okay. So this question, it states that a ball is projected horizontally from the top of a vertical cliff of height h. A steady wind blows horizontally to the left. Assume for simplicity the wind exerts a constant horizontal force on the ball equal to magnitude of its weight. With these assumptions, at what initial horizontal speed should the ball be thrown so that it lands exactly at the foot of the cliff? Okay, so this is our basic question. And one second. Okay, so it's given that we can just draw the basic figure. So we are given that a ball is projected horizontally from a height h, from a cliff, and its height is given as h. So this is suppose our cliff. This is the base of the cliff, and this is our topmost point, and its height is given as our h. And it is projected in the horizontal direction, horizontally, okay, and toward the left. And we have to find out what should be the horizontal speed so that the ball lands exactly at the foot of the hill. It means ball should be landing at the foot of the hill, that is at this point. Okay, so it is going to start from point A and it should end at point B. So this is the basic question. And the you can say it is also given that the wind exerts a horizontal force that is equal to the weight. Okay, so we have to remember this. So the wind, let us suppose it will be obviously towards our right, towards our left, traveling towards the ball, and let us suppose it exerts a force that is of Fw, and that will be equal to our mass of the magnitude of the weight, that is our mg. And so if we look closely, this will be our direction of our acceleration, and we can divide this acceleration into two components. Okay. So this is our point A, and this is our acceleration A. So one acceleration will be our a of x, and other one will be our a of y. Okay, so these will be our two accelerations. And a of y, obviously, because if we take a coordinate, so this is our x and this is our y. Therefore, we can write that we are having two accelerations, horizontal as well as the vertical acceleration. So we can say that our vertical acceleration and that vertical acceleration is our a of y, which will be equal to our minus of g, and we come to our horizontal acceleration, and the horizontal acceleration, that is our a of x, and that will be equal to our minus f upon m. And the negative sign only is our for retardation, because of the wind is in the opposite direction, and therefore it is going to retard. Okay, and this force we can substitute as our mg. So this comes over m, and this m and m cancels out, and this force is of nothing but retarding force, that is because of the wind. So therefore we can write that our a of x will be equal to our minus of g. Okay, so both are having equal magnitude. And now let us consider the vertical motion, and that is our so we are having our vertical motion, and for vertical motion we can write the equation as our y of t is equal to our h minus 1 by 2 g t square. And it is given in the question that the ball is going to travel from A and it should end at B. It means the vertical as soon as it is going to reach point B, this y of t will be equal to 0. Therefore we can write that ball hits the ground, which basically means that our y of t is equal to 0, and therefore we can write that our 0 is equal to over h minus 1 by 2 g t square, and from here we get our t is equal to 2h upon g and its square root. So this is value of time t it takes from point A to point B. Okay. And now we come to our horizontal motion. So we can write the general equation for horizontal motion, that is our horizontal displacement x of t is equal to our ut minus half gt square. And once again, as soon as it hits the point B, the horizontal displacement will be also equal to 0. Therefore, we can write that to land at the foot of hill, that is point B, our x of t should be equal to 0. So if our x of t is equal to 0 and time also we know, so we can just x of t is our 0 is equal to, we get this as u square root of 2h upon g minus 1 by 2, and this is t square, so this comes at 2h upon g. And this g and g cancels out, 2 and 2 cancels out, so we get our h is equal to our u square root of 2h upon g. And so we can find out our value of u. So we can say our u will be equal to h, and we can add this h square, so this will be coming as our gh upon 2 and its square root. So this is the value of our velocity, okay, which we were required to find out. Come to the next question. This question states that a ball is projected over a level ground with the initial speed u directed toward the east. A steady wind also blows horizontally eastward. Assume for simplicity that the wind exerts a constant horizontal force on the ball whose magnitude is equal to the weight of the ball. Under this assumption, determine the angle of projection theta for which the ball covers maximum horizontal range. And so this is the same question as we dealt in the previous one, but only difference is that it is projected on a and this is our u at an angle of theta. And so initially we have already, and it is also given that the wind is also flowing eastward. Okay, so both are in this. So the force because of the wind is equal to over mg, that we already know. Okay. And therefore we can write that our vertical acceleration that is of a of y will be equal to minus of g, and our horizontal acceleration will be equal to our a of x, and that will be equal to plus of g. Okay, we have already calculated how to find out this a of x. So they are equal in magnitude but opposite in sign. One will be downward and other one in towards our east side, that is our right side. And this u we can divide into two components. So this is your u of x and we are having u of y. So once again we are going to take both motion vertical. So we can say we are having our vertical motion And for this vertical motion, we can write a general equation, that is our y of t is equal to u of x times t minus our half gt square, and it lands back to the same level. So value of y of t is equal to 0. So we can just put it this equal to 0. And we can substitute the value of our u of x is our u cos of theta. So we get this as u cos of theta times t minus 1 by g t square is equal to 0. So this is basically quadratic in t. So I can write directly value of this t will be coming as our 2u sine of theta divided by g. So this is the total time it takes from point A to reach point B. And now we come to our horizontal motion, and so horizontal motion, we can write the equation as our x of t is our horizontal velocity, which is our u cos of theta multiplied by t, and this comes as plus half g t square. And we substitute the value of t, and let us denote that our maximum range, that x of t is equal to our r. Therefore we can write that our r is equal to u cos of theta, and we substitute value of t, that is our 2u sine of theta upon g plus 1 by 2g, and this is our 2u sine of theta g upon whole square. Okay. And a little bit of simplification is going to give us that our r is equal to, we can write this as our, this will be u square and u square, and 2u square by g we can take as common, and we will left with our sine of theta and sine of theta plus cos of theta. And we want to maximize the range, so obviously that maximization will be dependent upon this trigonometric function. Okay. Therefore we can say that r will be equal to our r max. Okay. And for that let us consider function f, which is equal to our sine of theta multiplied by sine of theta plus cos of theta. Ideally we can also consider this part, but when you differentiate it for maximization, this part is of no use. Okay, so we can simply ignore it. So we can find out the derivative of f with respect to theta, and that will be giving us our sine will be giving us our cos of theta, and the second function as it is, plus we have our sine of theta, and this will be giving us our cos of theta minus sine of theta. Okay, and we just open the bracket now. So this is quite simple now to solve it, and we are going to get, this will be sine cos and sine cos, that is our 2 sine theta cos theta, and we get this as a plus cos square theta minus sine square theta. And obviously we can put this equal to over 0, and we can further improve this. We can write this as our sine of 2 theta, our first part, and second one will be giving us cos of 2 theta is equal to 0. And now it is almost complete. And we get this as our tangent of 2 theta will be equal to minus 1. Okay. And value of theta will be our approximately 67.5 degree. For this value of our theta, we are going to get a maximum that when the wind is in support of our projectile motion, direction is same. Okay, projectile is also from left to right, wind direction is also from our left to right. A little variation can be also asked when the wind direction is in opposite part. Okay, so if this is the wind direction, okay, same question, but the wind direction is in opposite part. Okay, so in this case only one thing is going to change, that is our horizontal acceleration. That will be coming now as a minus of g. That will be the only difference, and accordingly rest of the calculation is also going to change. Okay, so we have to keep this in mind, that the horizontal acceleration is going to change according to our wind direction. Okay, so if wind is flowing on this, so here we are going to get our acceleration a of x will be equal to minus of g, basically retardation. Okay, and we can also you can say write or formulate it in a little bit different way also, and that different way that is not going to make much of the difference. And suppose the projectile is launched in this direction, okay, but wind is flowing perpendicular to this. Okay, wind is the perpendicular to the direction of the motion. So in this case, the only thing that is going to happen, that if without wind, suppose the projectile is landing at B starting from A, and if his wind is there will be a lateral displacement. Okay, so there will be a lateral displacement where this projectile is going to land. Okay, so this is our wind direction, that is perpendicular to the motion of our particle or our projectile. Okay, so in that particular case, we might be asked what will be the lateral displacement when the wind is perpendicular to the projectile motion. Okay, so projectile is flowing from left to right, and wind direction is perpendicular to this. So this will be resulting in a lateral displacement where the projectile is going to land. Okay, so yes, we can just calculate the lateral displacement. It's not a big of a problem. So the wind direction is going to ultimately affect how our acceleration is going to vary. So these were the 5 questions for today. Thank you.